Okay, everybody. Next up is measuring heat as it pertains to a phase change. Okay, phase changes are a little different because if you recall, phase changes do not involve the temperature change. All right, so we have a little problem with that because if we're using the Q equals MC delta T formula and there's a delta T in the formula, then that presents a problem. You probably could think about why. There's no temperature change during a phase change. If you remember from back a little while ago, if you learned this in your previous classes, you'll remember that the temperature remains constant. So that would have a temperature change of 0, and that wouldn't fit in the formula. So we got to find another way to do this. So that's the subject of today's lesson. So what we're going to do is we're going to look at phase changes and how you measure the heat going in and out of a phase change, and how much heat it takes to change the phase of a material. So we'll talk about that first. So we're going to use water here because basically water becomes what we want to do. Oops. So what we'll do is we'll look at water first. Okay, so first of all, water molecules are held together by intermolecular forces. So there's actually little forces that hold these water molecules together. And again, we can do a little drawing on this shortly. We can do that when we see it. So I'm going to get my pen together here. And then, so, okay, all set. There we go. Okay, so good. All right, so water molecules are held together by these intermolecular forces. Okay, and again, what we find is that heat is going to be absorbed or released when we break these intermolecular forces. When we talk about bonds being broken or bonds being formed or attractions being broken or attractions being formed, that's going to happen during these phase changes. Okay, so during this time, the temperature is going to remain constant. So if I talk about the phase change, so here's a little water molecule, okay, and here's a little water molecule, and there's a little water molecule, and here's a little water molecule, and again, we'll draw two of them, okay? Water molecules are stuck by these little attractions that are between them. So these are going to be made or formed during this phase change. So that's what you want to be aware of when this happens. But there's no temperature change during that time. So temperature is going to remain constant whenever this process is taking place. All right, so that's going to be important to know. All right, so the first things up is when we break the attractions apart in ice, or we go between a liquid and a solid of this. We're going to use the term the heat of fusion. So and it's going to be this value of 334 grams, 334 joules per gram. So that's how much heat it's going to take to break apart 1 gram of ice. So if we think of it this way, let's just say we have a little gram of ice in this little ice cube here, okay? And we want to make liquid water out of it. So I want to put a little heat on this. I'm going to melt it. I'm going to go all the way over here and form ice. What I'm going to find is in order to melt that ice completely, I'm going to have to absorb heat. Now, if I absorb heat, you will break apart these little water molecules in the ice and eventually liquefy them. And when you do that, you're going to have to add, which is why we have the plus sign here, 334 joules. And we find this by experiment. Okay, heat absorbed. So you can think about this being, yes, you guessed it, endothermic. Okay. So whenever you melt this, now what's interesting enough, if you wanted to go backwards, if you wanted to take the liquid water here and go backwards, you could guess what you have to do, right? Exactly. You would have to take out the 334. So really freezing and melting are kind of complementary here in the fact that you use the same amount of heat to do both, except that when you want to melt, you'll be adding 334. When you freeze, you're going to take out the 334. So again, heat release would be your exothermic change. Okay, so that's what we want to kind of, see in this type of this kind of thing. All right, so that's important to know. So we're gonna if you're doing 334 to 1 gram, then if you had 10 grams of ice, that would be 10 times 334. So we can end up with a little formula. And what we do is you say Q, which is the heat needing to melt or freeze, is going to be the mass of the water that you're using, okay, times the heat of fusion, okay? And this number is going to be always 334 joules per gram. And this is for water. Again, if you had a different substance, you would be using a different heat of fusion. Okay, so the heat of fusion is always that number. So that's a number you're going to have to know. Okay, so it's kind of easy to do. So to review, if you want to melt ice, you're going to have to add 334 joules per gram. If you want to freeze water, you're going to need to take out 334 joules per gram. Okay, that's the interesting part. So there's no temperature thing here because the temperature at this point is going to happen. This is going to be at, of course, this is going to take place at 0 Celsius, right? Okay, so depending on what you want to do. All right, so say we want to melt this. We want to melt. We want to actually go and do an example with this. So it says how much heat is required to melt 400 grams of ice at 0 Celsius. Now this is a little bit of a tease. I'm going to tease. You're going to get a tease here, and that's because they're giving you the temperature. So you may think that temperature is supposed to go in the equation, but be careful. Remember, it's at 0 Celsius, so it's not changing. Okay, so if the temperature is not changing, whoops, can't see that there, not changing, then you don't have to worry about it. So the key is melting. So melting tells us we're going to use that formula. So I'm going to take Q equals the mass times the heat of fusion. So I'll simply say Q equals 400 grams, okay, times 334 joules per gram. And again, if you dimensional analysis fans, the grams cancel with grams, and yes, we're lucky. We're stuck in joules. Okay, so I'm going to do this on my calculator right now. I'm going to take 400 times 334, and I'm going to get 1,000 or 133,600 joules. Okay, and let's just say I wanted to put that in scientific notation. I could. I don't have to do it, but I can go 1, 2, 3, 4, 5, and I would go 1.336 times 10 to the 5th joules. If I was doing significant figures, just to review, this number here only has one significant figure, right, in 400 grams. So I'm going to round this to one significant figure also, and I would get 1 times 10 to the 5th joules. Again, this answer is fine. This answer is fine. This answer is fine as well. So either way, however you want to do that. All right. So that's melting. Okay. The next part here is, what if I want to do the next phase change? So the next phase change would be vaporization, and it's kind of similar in a way to what we were doing before. It's just that the heat of vaporization is going to be higher. Okay. So what we're going to end up having is my heat of vaporization is higher. Instead of 334, the heat of vaporization is going to be 2260 joules per gram. All right. So let's just say I had a little bit of liquid water, okay, and I wanted to go and I wanted to turn it into a gas. So I not only wanted to just break the attractions a little bit like we did when we melted, but we want to completely rip them apart to a gas. Well, in that case, I'd have to put in 2260 joules, and I would vaporize it, heat absorbed, right? So that would be your endo. Okay. And if I wanted to condense it, I would go backwards, take the gas, turn it into a liquid, and I would have to release 2260. Okay. In that case, it would be exo. Okay. And this is exactly what happens in the atmosphere, right? When you take, gaseous water vapor in the atmosphere, and then you condense it to form clouds, you really release a lot of heat. So you can take H2O in the air, right? And then form a cloud. And a cloud, right? This releases a lot of heat to the atmosphere, okay, which causes the clouds to rise, more condensation taking place, and eventually you form a lot of clouds and you form a storm, and then that's what happens in the atmosphere with this heat. So, heat release in the atmosphere from condensation is a lot of heat. I mean, it's 2260 joules for every gram. Okay, so again, you would have this similar equation. The key again is this phase change, right? We're not getting this. So this HV being the 2260 joules per gram all the time. Okay, so that's a very similar kind of idea. So all right, so if you look up, unfortunately, there's a little problem here. Hold on. Okay. If I take a look at this, why this is not coming up, but if you take a look at this equation here, the problem here, how many joules of heat are released when 75.6 grams of water vapor condenses to a liquid, you can get an idea of what we mean. So what we're going to do is we're going to take, I won't be able to write it here, but you would simply use the equation. You would take 75.6 multiply it by 2260, okay? And again, you would get, I'll go back to the equation here. I know you can't see the problem here, but you would get Q equals 75.6, right, times the 2260 joules per gram, all right, and you would get 170,000, but actually 17,000, right, 85.6 joules. And you can round that to 17,086 joules. So that would be the answer to that particular question. All right, so that's how you'd find the heat of condensation. Or of course, you'd go backwards and forwards depending if you were, condensing water or you were vaporizing. Why do you think the HV is so much greater than HF? Well, if you had 2260 to vaporize, and this is 334 joules, right? The question is like, why is this so much greater than this? If you think about it a little bit, right? To rip apart these molecules completely takes a lot more energy than just liquefying them. Remember, a solid, you have the particles very close together, and when you liquefy them, you're kind of separating them a little bit, but they're still kind of flowing together a little bit. When you have vaporization, you're taking these liquid molecules that are kind of laying together in a puddle, and you're driving them completely apart, and that takes a lot more energy than you'd expect. Okay, than you'd expect for this one. All right, so it's interesting to know. We'll do a little bit of this a little bit later, and then we'll practice. So what you want to do is you want to practice the next couple of pages 10 and 11, are really practice pages on this. All right, so to review really quickly, you're going to use Q equals MC delta T, okay, when temperature change, okay? You're going to use Q equals MHV when you have vaporization condensation. So it's a phase change, right? Okay. And you're going to use Q equals MHF when you melt or freeze. So look for these words within the problem when you do this, when you do your problems. And again, we'll be able to do practice some of these in class. Bring your questions to class so we can do it in class. And then, of course, you can always come to the extra help sessions. All right. Have a great day, guys.